Dear student friends, in this particular topic, we shall have the discussion on what we call as mixed signal ICs and of course their applications. Right. So all of you know what is the meaning of an IC, integrated circuit. Right. Many things have been discussed about the ICs. We have seen about the analog ICs, right? We have seen about the digital ICs, the different gate circuits. Now, what exactly is the meaning of a mixed signal IC and how the very mixed signal ICs serve their purpose and what are its applications? That's what we are supposed to look here in this topic. And in this heading, we shall discuss about first on the phase locked loops, then analog to digital converters, digital to analog converters, and certain voltage regulator ICs. Okay. So now in this particular presentation, let us basically confine our discussion on the phase locked loop. Right? Let us try to see what exactly are the phased locked loops, and before that we will see the basic definition about the mixed signal IC. Now, the very word mixed signal, right, indicates that the signal which are either analog or digital, they are combined. The analog signals as well as the digital signals, they are combined here, right? An IC which has got the feature of both analog and digital ICs, right? It is referred to as the mixed signal IC. Now, your 7400 or 7402, 7408, these ICs are categorized as the digital ICs, like your multiplexer ICs and all, right? So similarly, you have so many analog ICs, IC 741 or any kind of such ICs, 555 timer, right? So these are all referred to as analog ICs. Now, if some IC has got the features of both analog ICs and digital ICs, obviously you would think what are the advantages. The most important advantage here is they share the common power supply, right? So now something is analog here and something is digital here, right? So you need not have two different supplies given here. With a single power supply, right, it is possible for us to have the operation of the IC. Now, having the single power supply basically reduces a lot of space, right? So you can realize a complicated operation in an IC which are both analog as well as the digital types within a smaller ICs, right? But unfortunately, and it is the limitation, it will be having a complex structure, right? So realizing an analog IC and a digital IC in a single IC is really going to be difficult and complex, and that is for only the manufacturers. It is the manufacturer's headache. Being an end user, right, you will be always having a certain IC with you. Only thing is that you should know how exactly you should use it, or what are the connection guidelines of these ICs, right? So these are the basic aspects about the mixed signal IC, which have got the features of both analog as well as digital ICs, which share the common power supply, reduced space, but slightly complex in operation. So this is what is the background on which we will be discussing about the very important IC of such kind. Right? It is a mixed signal IC, that is the phase locked loop, right? Now, the very meaning of this phase locked loop, it is a loop which is responsible for locking to a specific phase. In that way, it can be interpreted, right? So let us try to understand what are the principles or what are the basic definitions behind a PLL, where exactly this PLL is used. It is basically, in a very nutshell, you can consider as it is an electronic frequency control method. It is basically a frequency control method. Frequency control method means having the deviation of any frequency stopped, right? And you will confine the frequency to a particular value. In most of the cases, anyway, we will discuss about its applications later, right? It is too early for me to tell the applications now. First, we will try to see how exactly it is possible with the help of PLLs to have the frequency confined to a particular value or a particular range. And as you can see here, it is used for the purpose of frequency synchronization. You have got certain reference frequency, right? So you have some output frequency here which has got the tendency to deviate from here, but this very circuit makes it to confined to a certain range of frequency, which is considered here as the reference frequency, right? So now if you look at its generalized applications, right, not specific applications, they are very widely used in the communication systems, right, where there is a possibility that the frequency deviation might take place over the large range of traveling of the signals, right. They are also used in the navigation systems, right. They are used in the frequency modulation methods, and electrically speaking, in many motor control applications and all, right, we will have the application of this phase locked loops, right. Anyway, when you come to these specific applications of the motor control and all in your higher semesters, you should be able to appreciate these things in a better way, right. Now let us go into the very definition of the PLL, right. um, a feedback system that maintains a constant phase angle relative to a reference signal, and it can be used to generate high frequency output signals from a fixed frequency or fixed low frequency signals. This is what is the general definition. It's a feedback system that is basically meant to maintain a constant phase angle relative to a reference signal, right? So this is the basic definition of what a PLL is, right? So now, after taking that particular definition, let us go into the block diagram, right? We have already seen it is a phase locked loop, right? So this particular block diagram would tell us in a better way how exactly the very word phase locked loop, right, matches with this particular device. Now, if you look at this diagram, you have got one phase detector here. This is called as the phase detector. Then you have got a low pass filter here. Then you have got an error amplifier here, right? And here you have got your output signal. Let us say that this is your F0, right? With a voltage of say V0, right? Now this output signal is fed back to one more block which is called as VCO. This is nothing but voltage controlled oscillator. Voltage controlled oscillator, VCO. It's called as voltage controlled oscillator, right? So now the voltage controlled oscillator basically provides these signals, that is your F0 and V0, back to the phase detector. So the phase detector input is Vin or Vs, whatever you take, and Fs, that is the input frequency, right? And for the phase detector, the another input happens to be your F0 and V0. This is the general structure of how block diagram of PLL looks like. You have got a phase detector which gives certain output here, then that is passed through a low pass filter, then it goes to an error amplifier, and here you get the required output, and this output is again fed back to the phase detector through the voltage controlled oscillator, right? And this is the general structure. And now let us try to see how exactly this block diagram can be further explained in terms of its working. Okay, now we will go to the next slide, wherein we will be discussing about the principle of operation of a phase lock loop, right? So again, I have once again brought in the same phase diagram here. Now let us try to understand how exactly this works here, right? The reference signal and the VCO output, as I have already spoken in the previous slide, right? They are connected to the phase detector. So that means if you consider this as the phase detector, so this is going to be input and this is going to be the feedback signal. So this is your F0 and or V0, right? This is Fs or the input signal Vs here, right? So now this is going to your phase detector. Now what do you mean by a phase detector? Basically it is used to detect the phase of the signal. It can be simply an electronic switch like this. You can see here it can be an electronic switch here. I just represent the electronic switch, something like this, right? So now here, depending upon what you give here and what you take here as the reference, right, it gives the required output in the form of the error signal. Another simple example could be your what I draw here. You should be able to understand, right? A digital type of device, right? It is an XOR gate, right? So now suppose if you have an input signal, one of the input signals, something like this, right? Now let us say that the other input signal here, right, in this case say it is like this. Okay, now wherever there is a variation here between the input and output signals, that means when the input is 0 the output is 1, or when the input is when one of the inputs is 0 the other input is 1, right, you are going to get the signal as the output, the phase difference, right? Suppose if this is like this, now you can see here again you are going to get the output like this, right? So now these are the simple realizations of the phase detectors, right? So it can be anything. It can be an electronic switch, it can be a digital comparator, whatever it is, right? So now the output of the phase detector, after having received the two inputs here, F0 and Fs, right, the output of the phase detector is basically passed through a low pass filter and then it is applied to VCO. So the low pass filter basically, as we have discussed earlier, it passes the signals of lesser frequency. That means any unwanted high frequency noise signals or the disturbances, signal disturbances are present, they are going to be removed out. That is the purpose of using this low pass filter here, right? So then this signal is applied to one device called the voltage controlled oscillator, right? The voltage controlled oscillator, what exactly a voltage controlled oscillator does is, right, the phase of the signal from the VCO and the reference signal are obtained to get the difference signal error. This error corresponds to the phase difference, and this error signal is passed through the loop filter, which removes the high frequency signals. All these things we have discussed just now. Now the error signal is then applied to the VCO at its tuning voltage. This VCO, voltage controlled oscillator, I will explain more about this in our subsequent slide. But here the very basic function of the voltage controlled oscillator is to reduce the phase difference or to reduce the difference in the frequency between the two signals depending upon a voltage signal, right? So that is the reason why it is called as the voltage controlled oscillator, right? So its basic task is to reduce the difference in the phase or to reduce the difference in the frequency, right, by means of a voltage input. That is the reason why it is called as the voltage controlled oscillator. Now here you can see one IC I have represented, right? So this IC basically represents 566 VCO. It has got certain pins here, right? So now you have some voltage here, VCC, right, and ground for the purpose of the operation of the IC. Then you can see here you have got one capacitor CT and you have got one resistance RT. Then you have got here the modulation input. This is basically the voltage input, right? So now based on these things, that is your CT, RT and the modulation input, it is possible for us to make the output difference in the phases or the output difference in the frequency to be reduced based on these values CT, RT and the modulation input which it has received, right? So now the modulation input it receives through this, right? Now what this voltage, whatever you are going to give it to the VCO, it is basically the difference voltage, and this difference voltage makes the difference between the output signal as well as the reference signal as small as possible depending upon the requirement of the circuit. In this way, whatever the frequency deviations that you are going to have here, that is going to be reduced by means of the voltage controlled oscillator, right? So in this way, the output frequency, right? So here you provide the input frequency or the reference frequency. You've got too many elements coming into picture here in between where there is a possibility that the frequency gets deviated or the phase difference between the input signal and output signal becomes larger and larger, right? But this deviation is again brought into the normal value by means of this voltage controlled oscillator here, right? So this is what is the basic principle of working of your phase locked loop, right? You have a phase detector which has got a reference signal and also one of the external signals coming to here, that is the output. The phase detector output is given to a low pass filter. So the low pass filter removes whatever the noise signals or the high frequency signals are present in the input signal. Then it goes to an error amplifier. The output is fed back to the input or the phase detector's another input by virtue of the voltage controlled oscillator, where the voltage controlled oscillator tries to lock the output frequency with respect to the input frequency by reducing the error. This is how your the basic phase locked loop works. Okay. Now here one more important point to be noted here is it has got the three operating ranges. Of course, one is called as the free running mode. What I mean by the free running mode is, depending upon the physical limitations of the phase locked loop, it is not possible for the phase locked loop to track the frequency right from DC to infinity. It is definitely not possible, right? So therefore, there are certain ranges, right, of the frequencies to which your phase locked loop should be able to respond, right? Anything is beyond that, that is called as the free running mode. That time your phase locked loop will not be able to respond to those ranges of the frequency. Then we will come to the next one, that is called as the lock range, right? So the now if you take the diagram something like this, which is very much similar to what we have taken here, right? So let us say from a certain central frequency, let us say that this is going to be the lock range. This is called LR, lock range. Okay, these are the frequencies on either side of the central frequency of your phase locked loop, right? Now what exactly is this lock range? That's what we are supposed to understand. Once the PLL starts responding to the signal, so in this case the PLL does not respond to the signal, but once the PLL starts responding to the signals, right, it can track the frequency changes and the rate of, or sorry, the range of frequencies that are in the tracking ability of the PLL is called the lock range. As long as the frequency lies here or here, your PLL should be able to track those signals of those frequencies. This is called the lock range, right? Then the next one is the capture range. You can see here the next one is the capture range. Now once the lock range is identified, the PLL should be able to capture these frequencies within a shorter range. This lock range is a wider range, right? So now you will have to make the system frequencies to confine to either a single value or a small, range of the frequencies. That is what is the basic objective of your PLL. So now this is called as the capture range, the range of frequencies over which the PLL acquires the lock. right? So what exactly is the meaning of PLL acquiring the lock is the VCO changes its frequency until its output frequency is exactly equal to the input frequency. That is called as the uh, capture range. So definitely your lock range is larger than the capture range. Capture range is the smallest possible range. Smaller the capture range, better will be the performance of your PLL, because you will be able to confine the total system frequency to a very small range, right? So the capture range is a larger range, and another one is the free running mode, which doesn't come under the jurisdiction of the PLL. So it is beyond the range of the PLL. The same thing is represented in this diagram also. You can see here the unlocked range, right? Then the signals become like this. These are the capture transients, because in the process of the capturing, right? So there are certain variations in the signal ranges. Then finally, it is going to be locked here. This is how you divide the total operating range of the PLL into three categories. That is the free running mode, the second one is the lock range, and the third one is the capture range, right? For any given PLL, so the lock range and capture range are specified by certain equations. When we look at one of the types of the PLL, there we will come to know how exactly the capture range and lock range can be defined. Okay, now these are the general discussions about the PLL, phase locked loop, right, which is used to make the frequency of the signal not to deviate due to any reason. It is basically to make the frequencies to confine to certain range, right? Now, how exactly these PLLs can be realized, right? We are basically speaking about the uh, mixed signal ICs. Under the broad heading of the mixed signal ICs, we are discussing about the PLL. Now, I have mentioned about the low pass filter, I have mentioned about the phase detector, I have mentioned about the VCO. In the VCO, we have taken a separate IC also in our discussion, IC 566, right? So your phase detector can be anything like your XOR gate, right? So we have already discussed about the low pass filter. They are all the independent systems, right? So now, if you want to have all these things, embedded in a single IC, right? That results in our PLL ICs, right? They are called as the monolithic ICs, right? So whenever you have all these components in the block of your PLL combined or embedded in a single IC, right? Such ICs are called the monolithic PLL ICs. One of such ICs is IC 565. There are so many, manufacturers who manufacture these things, right? You have National Semiconductors, you have Signetics, right? You have so many other manufacturers, right, who manufacture these ICs, right? Now here, as per our requirement, we will discuss about one such IC, that is NE, that is NE or SE IC 565, right? So this is IC 565. We already discussed about IC 555 555 timer, right? So very similar to that, we will have the discussion about the NE bar SC, that is the Signetics or the National Semiconductor, right? So in a general way, we will discuss about that, right? So how exactly this particular IC 565 can be used as a PLL, that's what we will see here, right? So now in this particular case, let us first look into the features of this particular IC 565 IC. It's a 14-pin DIP, dual inline package. Its operating frequency is right from almost DC to 500 kilohertz, 0.001 hertz to 500 kilohertz, and its operating voltage levels are plus or minus 6 volt to 12 volt, and it receives an input level of from 10 millivolts RMS to 3 volts maximum, input impedance 10 kilo ohm, and certain aspects related to the bandwidth adjustment and all. These are not important for us. What is important for us is the operating frequency and the voltage level at which this particular IC 565 operates, right? So now we shall look into the very block diagram of this, and we will try to compare this block diagram with what the generalized block diagram we had earlier, right? So now please look at the block diagram of this IC 565. Okay, you have the phase detector as we had in the case of the general block diagram. We have got the amplifier, and here this particular combination C and R, right? This particular combination gives us the low pass filter, right? Then you have got the voltage controlled oscillator, and here you have got the VCO output, right? Now, very importantly here, so you can see here the output frequency of the VCO, right? When both the input terminals are grounded, that means when you connect these two to each other, short them, and when you ground them, right? The output frequency of this VCO is given by this particular expression. You will have to remember this expression. FC is equals to 0.25 divided by RT into CT. Very importantly, I have already spoken about the values of RT and CT earlier, right? So along with RT, CT and V, it is possible for us to have the adjustment of the output frequency with respect to the input frequency in the voltage controlled oscillators. That's what we had discussed, right? So now this RT and CT are the external resistances, right, which are going to be connected to external resistances which are going to be connected to pin number 8 and 9 respectively, as you can see, right? So generally the value of RT, right, it varies from about 2 kilo ohm to around 20 kilo ohm. So this is the acceptable range of RT as long as IC 565 is concerned, right? And generally the value of the capacitance, you can take it as 0.01 microfarad or any other standard value of the capacitor you can connect, right? Now the VCO free running frequency is adjusted with RT and CT to be at the center of the input frequency range, right? So we have already seen what is the input frequency range, right? FC here. Now, one more important point to be noted here is, very importantly, the total PLL, right? I will erase these things. The total PLL here, right? Now, it is split, okay? This is split, right, between VCO output and the phase comparator input, right? So now what I mean to say here is, if I connect this VCO output to the input here of your phase comparator, the phase comparator, as we have seen, this is one input, that is say pin number 2, another input, say this is pin number 3, this is 3, this is pin number 2. This is where the actual reference signal is going to be connected, to which the entire system frequency has to be locked. Now this 3, it is independent here, right? So now you can see here, if you connect 2 and 3 are the external inputs, that means you can connect 2 inputs here to the phase detectors, and one more input, that is the pin number 5 here, right? So that serves as the second input or the reference input here, right? So this reference input, now it can come from your VCO output, right? So therefore I said here you split this complete PLL IC into 2 parts. One is the phase detector and the amplifier, and the second one is VCO. As long as you connect this VCO output to pin number 5, now it is as good as providing this input to your phase detector. The another input, it could be either pin number 2 or pin number 3 depending upon the requirement, right? So now pin number 4 and 5 are to be shorted, right, in order to compare F0 with Fs, right? Now the capacitor C here is connected between pin number 7 and pin number 10, right, with an internal resistance of 3.6K. This is not going to be changed as long as you use IC 565, right? So this capacitor, this resistance will be always having the value of 3.6K. Now this capacitor C, right? So depending upon this is the external capacitor again, right? You can choose any value of the capacitance, 0.10 microfarad or 0.01 microfarad as per the requirement. So now this capacitor and the resistance R and C, right? These two form the low pass filter here, right? So in this way we have the complete operation of the PLL IC 565 here in order to realize the very basic purpose of what for the PLLs are deployed, right? So now if you look at the other expressions here, right? So this we have already seen, F naught is equals to 0.25 divided by RT into CT, where RT can be from 2 kilo ohm to 20 kilo ohm external resistance. CT is again 0.01 microfarad. So based on that, you will be able to decide the central frequency of the PLL 565, right? Then you have got two more ranges of the frequency as we have discussed in the earlier slide. One is called the lock range, right? So let us say that your lock range is somewhere here. This is called LR, the lock range, LR, okay. The lock range is given by delta FL is equals to plus or minus 7.8 F naught divided by V, where V is the supply voltage. I have already told you that this supply voltage can vary from plus or minus 6 volt to plus or minus 12 volts, right? So this plus or minus indicates that the lock range varies on either side of FC, right? So similarly, the capture range, right? All these things have got their own derivations and all. Anyway, we are not going into the derivation part of it, right? So now if you look at the capture range here, this is given by 2 into delta FC, where your delta FC is the capture range, right? 2 into delta FC is equals to root delta FL divided by 2 pi RC. Since the value of R is already known to us, that is 3.6 kilo ohm, I have taken it to be 3600 into C, right? So this is what is the expression for the capture range, and also the expressions for F naught and the lock range we have seen for the case of IC 565, right? So now with this particular background, let us now go into the applications of the PLLs, which I have generally mentioned in the beginning, but in particular, what are the different applications that we have in the PLLs that we will see here, right? The first one is the frequency multiplication bar division, right? So whenever you have got certain frequency, let us say that I have got 100 hertz, I want to divide it into 20 hertz. I mean, I want to divide it by 5. Suppose if I got 500 hertz, I want to make it 2000 hertz. That means I have to multiply it by 4. So whenever I want to have the frequency division or multiplication, the PLLs are one of the simplest here. What you can do here, you can see here, you've got a phase comparator, you've got LPF, amplifier, VCO. These are all the parts of your PLL. Now, beyond that, generally what we do is we connect VCO output directly to the one of the inputs of your phase comparator. But here, what we do is we make use of a divide by N counter, right? So whatever F naught you are having here, that we feed through a divide by N counter. So therefore, whatever we have here, that will be F naught divided by N. So in this way, we will be able to have the output F naught is equals to N into Fs, right? If your Fs is say 100 hertz, and if your N is equals to say 4, we will be able to get a 400 kilohertz here, right? So like that you can have the frequency division also depending upon the value of the n, which is selection, right? So this is one example which I have taken. Like that you can have the different applications, right? Like the amplitude modulation detection, the frequency modulation demodulation, right? Then you have one more application called frequency shift keying, right? So this is also one important application of your PLL, that is called as the frequency shift keying. These are all coming in your electronic circuits, right? What exactly is the meaning of the frequency shift keying and all? When we discuss about the communication circuits, that time probably we will be able to understand these things in a better way, right? So therefore, basically here the applications of PLL, right? If you look it from the point of engineering, I mean the electrical engineering, right? So we also use it for the purpose of the motor control. Whenever there is a deviation in the frequency, as long as an AC motor is concerned, right? If you want to synchronize the frequency of the motor with respect to the system frequency, then the PLLs are used. They are used in the FACTS devices, flexible AC transmission system devices, in order to have the proper monitor over the frequency, in order to avoid the instability of the system and all. Of course, all those things when you come to our higher semesters, right, you will be able to understand, right? So these are certain applications: the frequency multiplication and division, the AM detection, the FM demodulation, frequency shift keying, the motor control, and so many other applications are there, as long as we have the uh, PLLs, right? So now with these things, let us look into a simple example here at the end, right? How exactly we will be able to solve this example, we will see now, right? Um, Compute the free running frequency, lock range, and the capture range of PLL IC 565 for RT is equals to 20K, CT is equals to 0.01 microfarad, C is equals to 1 microfarad, and supply voltage of plus or minus 6 volts, right? So this is what is the simple example. You please bring the diagram back to your mind, right, which you have discussed a couple of slides before, right? So here the value of RT is given, the value of CT is given, the value of C is given, and the supply voltage, whatever you are going to give to your PLL, this is given to be plus or minus 6 volts, right? And we have got the formula also to calculate the value of first F naught, that is equals to 0.25 divided by RT into CT. If you substitute the value of RT and CT in this particular expression, right, you would get 0.25 divided by 10K into 0.01 microfarad. That will give you somewhere around 2.5 kilohertz as the answer for F naught. That is the center frequency, right? If you take it like this center frequency comes to be somewhere around 2.5 kilo ohm, right? Then if you want to take the value of the lock range, which is delta FL, we've already seen the formula for a lock range, that is plus or minus 7.8 into F naught divided by V, right? So if you substitute plus or minus 7.8 into F naught is 2.5K divided by V, that is 12 volts, right? Plus or minus V means plus V minus V, that becomes 12 volts. So you get around 1.62 kilohertz, right? So now 1.62 kilohertz means one this side and on the other side, right? So plus or minus 1.62 kilohertz on either side. If you take this as the frequency scale, now this frequency will be 2.5 minus 1.62, and this frequency will be 2.5 plus 1.62, right? That is 4.12. This comes to be 4.12 kilohertz here, right? So if you add 2.5 and 1.6, so this becomes 2.5 minus 1.62, whatever it is, you please calculate it and put. So this is going to be your lock range. This is going to be your lock range. Okay. Then the last one is the capture range, that is 2 delta FC, 2 into delta FC. So this we have already taken the formula under root delta FL divided by 2 pi into 3.6 into 10 to the power of 3, right, into what is the value of the capacitance? 1 microfarad, 1 into 10 to the power of minus 6, right? If you substitute here, this you get somewhere around 378 hertz. So now this is going to be the lock range. So 378 on either side, this is going to be your capture range. Sorry, this is the capture range here, right? So now you can see here, definitely the capture range is much smaller than the lock range. So this is one simple example by means of which you can understand what is the center frequency, what is the the lock range, and what is the capture range. And you also understand that your lock range is much larger than the capture range as far as PLL IC is concerned, right? So now this is one simple explanation regarding the PLL. What are the basic PLLs, right? Where do they serve their applications, right? How do you realize the PLL, right? How do you have the principle of working of PLL? Then what is the block diagram, right? What do you mean by the phase detector? What do you mean by the low pass filter? Then the error amplifier. Most importantly, what is the feedback signal that is again given to your the phase detector through the voltage controlled oscillator? How do you realize all these things independently and in a single block or in a single IC? How do you realize all these things, which called as the mixed signal IC here, right? So basically this IC 565 is one of such ICs which is called as the PLL ICs. This is also one of the analog building blocks similar to what we have seen in the case of IC 555 timer. Okay, and how exactly IC 565 operates, right? What is the significance of RT? What is the significance of CT? Then what is the significance of the voltage? How do they decide the output of the voltage controlled oscillator to be tracked to the reference signal? Then how the low pass filter is realized here, right? Using the external resistance, the fixed resistance component and the external capacitance, right? And how we can look into some simple numerical examples we have seen here, right? So now in our next discussion, we will go with the discussion about the digital to analog converter. Okay, we'll stop here. Thank you.